Hi everyone, thanks for joining us today for another Australian fluid mechanics seminars. It's my pleasure to introduce our today's speaker, Dr. Esteban Ferrer from University of Madrid, University of Madrid. He is the associate professor in applied mathematics at the School of Aeronautics at University of Polytechnic of Madrid, and he got his PhD from Oxford University with 2 masters, and he joined industry before joining university, and he has 18 years experience in the field of numerical simulation and instability analysis. And he's going to give us a talk on Let's Get High. With this, I hand it over to you, Esteban. Thank you.
Thank you very much. Thank you for the invitation. So, okay, what I thought I will talk about today, it's the recent developments we are doing in our high order solvers, right? So, and hence the title, Let's Get High. So I will try to explain a little bit what the recent developments basically. So I would like to thank my collaborators. I would like to thank, well, and basically what we do in the department of applied mathematics at ETSIAE in Madrid is we develop incompressible and compressible solvers. We focus on high order methods and especially on discontinuous Galerkin, but we're also working a little bit on flux reconstruction and other methods. We also develop stability sensitivity tools, and then we are coupling this for enhancing flow control, for trying to do flow control over a variety of configurations. We apply these kind of techniques, both high order and flow control, to aeronautical applications, to wind and tidal turbines, and to multiphase flows. So I will show a little bit of everything in this talk, I think. Right, I would like to thank my PhD students, the current students and the past students, which you have here, and also acknowledge the funding of mainly European funding here at the bottom, a couple of European projects. Also acknowledge some industrial partners with whom we have collaborated in the past and in the present. Right, so let's go to the summary. The summary, I will give an introduction on why we want to do or use high order methods, and in particular discontinuous Galerkin. Then I will start mentioning the multi-physics we are adding to our solvers, right? So we are making things more complicated. We're solving more and more complex physics. I will cover moving meshes with sliding meshes, Immerse boundary methods, multiphase flows, turbulent and narrow acoustics. And then in a second part, I will talk briefly about the acceleration techniques we are including in our solvers to make things more efficient, right? So this is mesh adaptation, local mesh adaptation, matrix forming techniques, and multigrid methods. Right, so briefly on high order methods, why are we interested in high order methods? So the idea is in low order methods, you have a mesh fixed, for example, here 3 triangles, okay? And then you have a low polynomial order, a piecewise constant, infinite volumes, or piecewise linear variation inside each of the triangles. And this is your method. So if you want to increase the accuracy in your numerical solution, what you need to do is to increase the number of triangles. In high order methods, we have the possibility of increasing the polynomial order inside each of the triangles. So we can go to polynomial order 2, polynomial order 3, or any polynomial. So there's another way we can fix the triangles and we can increase the polynomial to get a more accurate solution. So we have 2 ways to improve the solution accuracy, right? One we call edge refinement. This is including more and more triangles. The other one is peer refinement, which is increasing the polynomial order in each of the triangles. So in addition, discontinuous Galerkin allows for discontinuities in the numerical solution, so we can have gaps between elements, right? Inside each of the triangles, the solution is continuous and captured by the polynomial. Between boundaries, we allow for discontinuities, as opposed to continuous Galerkin, where everything was continuous and forced to be continuous between elements. Now in DG, in discontinuous Galerkin, we can play around with the fluxes between elements to make things more or less continuous, right? So we can allow for gaps, or we have some parameters that we can play with, and then we can make it a bit more continuous. And then I will show some examples of how we can use that in our favor. Right, so why would you increase the number of triangles, or why would you increase the polynomial? So what's the deal there? So the idea, I think it's quite clear in this case. So this is a very simple Poisson equation, so an elliptic equation, where we have plotted the number of degrees of freedom in the x-axis and the relative error norm. So we know the exact solution, so we can plot the error. Right, so what we've done is the different colors are different meshes with different number of triangles, from 32 to 128 triangles, right? And in the boxes, we have the polynomial used for each of the simulations, right? So if we do edge refinement, that is keeping the polynomial order fixed to a low order, for example, 2, and we increase the number of triangles, we see that the error decreases along this line. However, the other possibility is to fix a very coarse mesh, for example, 32 triangles, the red one, and increase only the polynomial order without changing the mesh, right? And then the error decreases like this. We go from P2, P3 to P7, right? So the idea is that when we increase the polynomial order, the error decreases much, much faster. It decreases exponentially, whilst when we're using a low order method, so for example, a fixed polynomial of order 2, then the error decreases much more slowly. What this means that if we want to achieve a certain level of accuracy, let's say 10 to the minus 7, we will use fewer degrees of freedom with a higher order method, with polynomial order 6 on a coarse mesh, than if we use a low order method on a very fine mesh, where we will need many more degrees of freedom, which results in bigger matrices and larger systems to solve. Right, so this is the main idea of higher order methods, that we can achieve higher accuracy, right? And how this translates into a real case, a more realistic case. So if we check the flow after an airfoil, what we see is if we use a low order method, like planet volumes, a commercial called fluent second order, on a fine mesh, we see that the flow field and the structures after the body, they get dissipated quite fast, and this is because of the numerical errors of the low order method. However, if we use a higher order method, polynomial order 5 here, on a coarse mesh, what we see that the structures are kept unchanged, so are well captured, even in this coarse mesh. Right? So what we see is that the inherited low numerical errors are kind of visible in simulations that we really perform in a day-to-day basis. Right. If we go to turbulent flows, we can also see similar ideas, right? So if we compare a DNS simulation published here in 2003, and we compare that to a RAN simulation on the right. So this is a low order method with a steady RAN simulation, K-omega SST model, again with Fluent. What we see is that we're losing many of the structures of the flow field. We still see the overall shape of the separated region, but we're missing a lot of structures. However, when we go to a very coarse mesh, you can see here in gray the underlying mesh, with a polynomial order 5, what we see is that we do capture a decent amount of flow structures in the separated region, right? Showing the potential also in turbulent flows. Right, so typically when we go from low polynomials P2 to polynomials order P3, what we see is that when we increase the polynomial, we see more defined structures. So before P2, maybe we see a blurry separation region, and in P3, we will start seeing some better defined vortices and things like that, right? And that we see over and over in different simulations. So we get more definition in the flow structures. Okay, another way of looking at the properties of higher order methods is to use von Neumann analysis. So von Neumann analysis, in a nutshell, what does it compares the continuous solution with the discretized solution, right? For an advection diffusion equation, or in general, we typically check just advection, right? So by comparing the wave, which is the result of solving the continuous equation, to the numerical wave that comes out from the discrete equation, comparing these two, we can see if one is damped with respect to the exact, then we get this dissipation, and if one is shift in phase, then we see some dispersion error. Right? When comparing the exact, in this case, just advection, So just linear advection. So the advection solution, it's just this linear slope. Of course, it has no dissipation, so that should be 0 exactly. And then we compare that to the numerics. We see this kind of behavior. We see that the errors, so the errors will be the difference between the numerical and the exact. Those are confined to the high wave number region, right? So that means that for low wave numbers, we are really capturing the real solution, and the errors are just confined to the very high wave number region, right? Which are good properties, because it's exactly what you want if you want to compute LES or something like that, right? Turbulent flows. Right, so higher the methods, then another way of looking at them, it's we normally we have very high, very large elements, but inside each element we have the polynomial. So we can look at the points used to fit this polynomial inside each element to give us a sense of the real mesh that we are using, right? So typically we will see very large elements, but inside you have to think that there are polynomials used to the points used to define the polynomial order, okay? And this gives you a sense of what is the real mesh that you're using. Right, a thing that I'm not going to talk about today, but I just mentioned it, is that in high order methods, we need to use curve boundary conditions, right? So if you're using this very large element, you want to capture the curvature of the airfoil because of this large element, and you're using a high polynomial inside to capture the solution, so you need to use curve boundaries. And for this, if you don't do that, you get these kinks in the pressure and shear stress. But if you do, you get a smooth solution, right? And this is what you want. Right, so we're able to solve a variety of problems from I don't know, aeronautical applications, wind turbines, I don't know, many things, turbulent laminar flows, etc. But still, we have to mature them a little bit, okay? And this is what I want to talk about today. So currently, we are developing, we're putting our efforts in a tool which is called Horses 3D, right? That you can have a look at this thing. You cannot download it, but if you ask us, maybe we can talk about it, right? And well, in a nutshell, we are developing all these things. So we have turbulence models, we have compressible, incompressible versions, we have multiphysics that we are including, and I will talk about this today. Right, it's based in this continuous Galerkin formulation, and for efficiency we use quadrilateral hexahedral elements basically. Right, it's parallelized, so we get quite good performance up to, I don't know, we have tested 1,000 processors, right? And especially what I think is interesting is that when we combine MPI with OpenMP, so this is parallel processing with multi-threading, we get a lot of advantage, especially at high order, right? So if we go to polynomial order 6, we see very good scalability, right? So the curves get very close to the ideal scaling, right? So we try to take this into account and to use well, this in our favor, right? So higher the methods, the higher polynomials are good for accuracy and they're good for parallelization. Now, let us see how they scale, right? So how they scale in terms of cost. So if we look at the cost, other high order techniques were often criticized because they were very costly. So, okay, the error was decreasing very fast, right? Exponentially. The error was decreasing exponentially, but the cost also was increasing exponentially. So there was no real advantage of doing it because, well, they were very costly. So with this particular version that we use, which is based on Kopriva's book, what we observe is that we have exponential decrease of the error, but only a linear increase in the cost, right? So we have run recently quite a few simulations on wings like this. So there are turbulent simulations in a variety of architectures. So we have a variety of MPI processors and also multi-threading, etc. And we typically observe for various meshes, various polynomials, etc., that we increase the polynomials, right? So we're going along these curves. We're going along these curves. So this is increasing polynomials, right? So this is a fixed mesh, fixed edge mesh, fixed edge mesh. But then on the mesh, we are increasing the polynomial order to increase the degrees of freedom. What we see is linear scaling, right? So you can see here the fitting, and they are linear. They're not increasing exponentially, which is good, right? It's good because the error does decrease exponentially. Right, so this is the introduction, this is the motivation, right? So of course, I'm saying we have solvers that are quite mature, but what do we want to add? So that's the idea. What's the remaining challenges? So I will start talking about moving meshes and how we can handle moving meshes, right? In particular, we'll talk about sliding meshes and immerse boundaries. Right, so sliding meshes, it's just when some part of the mesh can move and another part of the mesh stays static, okay? So the idea here is that the interface between the two, so this is this region here, doesn't have to perturb the flow that goes through it, okay? So as you can see here, there's no noticeable change in the contours, so they don't care there's an interface there, right? And that means that the errors, the local errors there are small and we are capturing things properly. And we've used that in the past, the hanging nodes with the higher order methods to simulate wind turbines and tidal turbines, such as those. Of course, before computing anything, we want to check that we're not losing this exponential convergence, so this decay of the error when we increase the polynomial order, when we use hanging nodes and when we have curved inner meshes, right? So we have checked that, and indeed we recover the exponential convergence that we should get also with a mesh which is very typical, with no hanging nodes or anything. Once we have validated that, then we can use with confidence this solver to solve, I don't know, more interesting physics, right? So for example, how in a vertical axis turbine, the vortices shed in the front passage will perturb the airflow when it goes through the rear passage, for example, right? We have studied this in this publication at the bottom. Right, we can do that in 3D, and then we get some interesting wave flows, and that can be also used for analysis. Right, these moving meshes, so these sliding meshes are interesting, but they still are a bit costly, right? So recently we have moved towards immerse boundaries. So immerse boundaries are an interesting method because they are easy to implement and they provide interesting results. So here you can see some examples. In this particular version of the immerse boundaries that we've chosen, we only need to include a penalty term, so a source term in our Navier-Stokes equation. So those are our Navier-Stokes equation. We only need to include a source term of this form, where we set inside the body, only inside the body, the velocity field of the momentum, the x momentum, y momentum, etc., and the energy values to 0. Okay, and this we do by penalizing. So we add a penalty parameter that forces the velocity inside the body to be the one we want, right? If the body is static, we set it to 0. If not, to the moving body, the velocity of the movement, right? So this is quite easy, straightforward to implement. And when combined with higher order methods, what we observe is that we don't lose the properties of doing p-adaptation. So when we adapt the mesh, when we increase the polynomial order, we are getting a more accurate solution. So it pays off to combine immerse boundaries in this form with higher order methods. Right, a very recent development, right? So it's still under review. It's to play around a little bit with these penalties, with these forcing terms that drive the velocity to 0 inside the body, right? So one possibility that we have, and to increase the accuracy, right? So one possibility is to add a second order term like this, in addition to the first order term that penalizes the solution. And then when you do so, we found that you can, there are optimal values for the combination of these two parameters, right? So these two penalties that you get here, they can be combined in a precise way such that you get a minimum error, right? Furthermore, when you decrease the error, how you combine those appropriately, you can also increase the time steps that you can use in your method, right? So you get smaller errors and higher time steps. So there's a lot of potential, we think, in doing things to improve this kind of penalty method, right? Especially in the context of high order methods. And this is what we're doing. We're doing other ideas, but those are still in development. Right, regarding multiphase, so multiphase flows, there's a variety of multiphase flows that one can use. A well-known one is the volume of fluid, but we choose to use the phase field model. So in the phase field model, what we consider is a dispersed interface between the two fluids, right? And that's kind of convenient because when we use a higher order method, we don't get sharp discontinuities, which are not very suitable for higher order, because you might get Gibbs phenomena. You might get oscillations at this sharp interface. So the diffuse interface avoids this problem by having some small thickness into the interface. And this can be done through the Cahn-Hilliard equation. So we couple Navier-Stokes with Cahn-Hilliard, and by doing this, we can have different phases and things like I'll show you in a minute. Right, so we've coupled Cahn-Hilliard with the incompressible Navier-Stokes, right, and we are able to solve a variety of problems such as those ones here. One thing that we are doing right now is to add the possibility of having p-adaptation into to track the interface, right? If you track the interface with p-adaptation, can increase the local number of degrees of freedom at the interface, which makes simulations much more efficient as compared when doing a global adaptation. So we're seeing advantages of 50%, and that's including the cost of doing the adaptation, which has some cost, but still we get improvement in 50% on efficiency. Right. Also, in the context of an industrial collaboration, what we did is we include some wall models into this multiphase flow to account for pipe flows. Right. So as you can see here, and then I'll show you some examples. So what you can see is that then by changing, for example, the velocity of the phases as they enter in the pipe, we can see interesting physics, right? So we can see how one flow separates the other one here at the bottom, and one tends to creep and get annular around the pipe. Right. What we had to do though to get these nice figures is to use an energy stable scheme, right? So in a nutshell, energy stable or entropy stable, sometimes they call, follow this idea, right? So normally you have your Navier-Stokes equation, which are conservation equations, of course, of momentum, right? But you don't explicitly solve the kinetic energy equation or the entropy equation. Now, the continuous equations, they do fulfill the kinetic energy equation and the entropy equation, right? So the continuous equations, you can show that they fill this additional equation, although you're not solving them. Right, so the idea of the entropy stable version of the numerical scheme is that, okay, let's get a numerical scheme that, in addition to solving the continuous equation that I have to solve to get my flow field, in addition, also conserve energy and also conserve entropy, right? So if these equations also conserve energy, also conserve entropy, it's much more difficult that they blow up because there's no buildup of energy possible, right? So you are conserving energy. And this is the idea. So let's mimic the behavior of the continuous equation in our discrete equations, right? This translates into using particular details into the numerics. In particular, we use SBP, SAT methods, okay? And I will only mention that they use Gauss-Lobato points. So you have to shift from typical Gauss points, which are inside the element, to Gauss-Lobato that include the edges. And this will be interesting later during the talk. Right, in any case, if we use entropy stable schemes, we're able to stabilize simulations that were not stable otherwise, okay? So for example, you can see here, for this very smooth flow, we didn't have any problem neither with the standard DG or with the energy stable scheme, okay? However, if we go to a more complex flow where we get a problem, we get the interface moving and we get some under-resolved features at the interface, what we see is that the standard method blows eventually, but the energy conserving stays bounded, right? And provides you a solution. And so on. We can increase the complexity. This is always by changing the velocities, the relative velocity between the phases at the inflow. Then we get also blowing for the standard and non-blowing for the energy state. So it proves advantages to do this to derive new schemes that are energy stable or entropy stable for new methods, right? And this is what we tend to do. It's a bit tedious. You have to do a lot of analysis, but it pays off. Right, regarding turbulence, I will try to show you some, we think, interesting ideas, not the classic methods, okay? So the ideas go through exploiting these properties, numerical properties of high-order methods, right? Where the errors are confined to the high wave numbers range and things like that. And for this, what we do is we exploit the numerical errors in our favor to develop new turbulence models, right? So basically, those are typically called implicit LES. Implicit because you don't have an explicit definition for the subgrid scale, but you use the numerical errors to do that job for you, right? For a method to be suitable for implicit LES, from our perspective, you need to first know how the numerical errors behave. So this is doing some for Neumann analysis to see these curves and and hence to know where your dissipation is acting. So at high wave numbers, for example, you might want to have some dissipative character. So you want dissipation at these under resolved high wave numbers. And of course, it has to have the errors have to dissipate energy at the correct wave numbers, right? So in a DNS simulation, we're solving the whole energy cascade, okay, from the Taylor scale to the Kolmogorov scale. So you have the whole cascade of energy. But in LES, what we're doing is we're truncating this cascade at some point, right? So because viscosity only can act at the Kolmogorov scale, if you don't do anything, what you will have is an accumulation of energy at these cutoff wave numbers, right? Because you don't have any dissipation mechanism acting at these wave numbers. This is in an ideal scheme where you don't have any errors. Of course, what you want is your errors or your explicit subgrid model to dissipate energy at this range. Right, so we could say that a good numerical behavior for LES will be the one that follows very well this curve here, and then suddenly near the wave number, the cutoff wave number, it adds damping, right? And it damps the energy and drains energy at this particular scale. A bad method for LES is the one that adds dissipation before the cutoff level, right? So brings the curves down here where they shouldn't. You should be able to capture this. And then it doesn't add enough at the cutoff wave number, right? So it's important not only to have dissipation in the numerics, but where this dissipation, at which scales it's acting. Right, so I'll show you some ideas on how you can increase dissipation and in the right place, okay? So I'll show you 3 examples, in fact. In the Navier-Stokes equation, if we look at the Navier-Stokes equation, I think there's 3 places where you can add dissipation or numerical dissipation, right? The first one is the Riemann solvers. So this comes from the nonlinear advective fluxes, right? And how you discretize those. So people have looked at that in the past, so we're not rediscovering anything. I'll show you a small example, right? So this is how you play with the flux, the Riemann flux, which can be Lax-Frederick or Roy or whatever flux you want to use. This is one possibility. Second possibility is to add some artificial viscosity, right? When you add artificial viscosity, typically it's called explicit LES because you're adding some subgrid scale, right? And I will show you an example of this as well. And lastly, you can also play around with the viscous terms. So how you are discretizing the viscous terms without adding any additional dissipation, right? So everything comes from the discretized version of the viscous terms, right? And we've played with all of those. So let's start with the first one. So in the first one, this is, I mentioned that it's classic because people have played around quite a bit with this, right? So we can, for example, simulate the Taylor-Green vortex, which is this evolving turbulent flow inside the box, okay? And then we can cut at certain point of the evolution, and then we have this kind of nice spectrum, right? So if we play around with the fluxes, the convective fluxes, we can, there's a parameter lambda that can control the dissipation we're adding into this flux, right? So if we play around and we take a large range from 0, 1 to 10, we're able to add or subtract a little bit of the dissipation from these Riemann solvers. So what we were seeing is that even if you increase lambda by a large amount, you are stuck into some maximum dissipations you get. Okay, so basically, in this case, we were able to change a little bit the spectra, but not a lot, right? So we were able to change a little bit the very high end of the spectrum. So that particular version of the Riemann solver acts at the very high wave number range, right? So sometimes for other Reynolds numbers, we might need other mechanisms to, in addition to this one, supply more damping at the right scale. Right. So in that same paper, right, which is this one here, we developed an artificial dissipation, right, to compensate for these advection fluxes, right, when there wasn't enough dissipation at a smaller wave number. Right, so to do that, what we started with a Smagorinsky viscosity, but in addition to the Smagorinsky viscosity, which will act basically in the whole spectra, right? It's not focusing on a particular wave number range. We included this Smagorinsky together with a particular kernel that allows you to switch in wave number, right? To locate this particular viscosity at a particular wave number, right? So this idea is not new. It's called spectral vanishing viscosity idea, right? And the kernels can be of this form, right? So for example, we took the one by Mora, and then combining this, we were able to first study in the von Neumann analysis how this additional viscosity was acting, and we saw that was at the mid-range of the spectra. So we have more control over what was going on in the whole not well resolved range of wave numbers, right? And then when we use the Taylor-Green vortex again to check, we were able to tune a free parameter that basically tells you at which range of wave numbers we are acting to really match the theoretical solution, right? So we're able to tune this parameter, and we've tried with other flows, and it seems that this tuning seems okay for a range of polynomials, etc. We're not saying it's the complete truth, but so the complete answer to turbulence, but I think it's a nice way to go. Right. Finally, example number 2 will take into account the discretization only of the viscous terms without any additional dissipation. Right. So in this particular case, I will switch to the incompressible Navier-Stokes equation. Right. So if we take the viscous terms in the incompressible Navier-Stokes equation, so this Laplacian operator, and we discretize it, right? In particular with DG, we can use interior penalty to discretize this term. What this gives us, it's a matrix. We don't care about the details, but an additional term that depends on a free parameter, which is called the penalty parameter in the interior penalty. So because we have freedom in choosing this free parameter, we can see what happens if we drive this equation towards the limit of very low viscosities or the invisible limit, right? So the very high Reynolds number, to see what's the effect of this penalty, of this additional term. So what we can see is if the viscosity tends to 0, this term cancels, and we end up with this product of the viscosity times this free parameter that we have, right? So if we make sigma, this free parameter, proportional to 1 over the viscosity, what we get is that this term will not cancel in the limit of very high Reynolds number. And this term, we'll look in a minute at what this term is. This term provides a little bit of stabilization, even in the invisible limit when we use the incompressible Navier-Stokes equation. Right, so what is this term? This term is a term that has this penalty, this free parameter, but has also the jumps in the numerical solution. So the jumps are in this continuous hierarchy, these jumps here in the numerical solution, right? That we can vary more or less at will, okay? But what's interesting is that these gaps, so these gaps that you get in the numerical solution are proportional to how well or badly captured is the solution, right? So for very fine meshes, we get no jumps, right? For very large meshes, we get a lot of jumps, okay? So they are proportional to how well or badly we are capturing the solution. Hence, making this term proportional to the well or badly capturing the solution, making it proportional to the local viscosity you're adding, it's a very nice LES model because you're adding viscosity only in the badly resolved regions, right? And you're not doing anything in the well-resolved regions where the jumps are 0, okay? So we thought that was an interesting way forward, right? So for example, if you test this effect on adding some noise in your initial solution, what you see is that if this penalty term is small, you don't make it proportional to the viscosity, things blow uncontrollably and that goes crazy. But if you make it proportional to the viscosity, everything stays under control, right? And the solution stays bounded. Right, of course you can run classic cases and you get kind of good accuracy. And in fact, this particular model is the one I used to solve this plot here that I showed you before. Right, we can also do it in rotating meshes because we have this sliding mesh technique. And then when we compare to fluent simulations, to lower the methods, what we see is that the flow field is completely different. So we get a much more rich flow when we use the higher the method. So quite a few vortices, shedding, etc., that you completely miss when you do a lower the method. Right, and that translates into the forces. We can see that the forces, when compared to experiments, right? So the forces are quite okay, well captured for the higher the method, but with the lower the method, we have some gaps here related to not well capturing this water shedding. Right. So in the next two slides, I'm just comparing the two higher the methods, or the two of the possibilities that we saw. One is the interior penalty penalization, the one I just mentioned, and the other one is all this machinery with the energy stable fluxes and etc. Right, the compressible version also. And we saw a good matching with experimental values for lift and drag. When comparing both solvers, so both solutions, we see quite well matched, right? And this is adding dissipation in a very different way. So very different ways, but with the same background idea. The background idea is to do it at the right place. Okay, so we're able to see these kind of effects. Right, I'm just going to jump ahead. Right, so we're extending these implicit LES ideas to other methods, and I'll briefly mention one. For example, we've extended that to lattice-Boltzmann methods. So in some particular versions of lattice-Boltzmann, which is not the classic, so the BGK is the classic one. There's other versions of lattice-Boltzmann where you get some free parameters in your model, and these free parameters can be tuned at will. So we choose to tune these parameters such that we get dissipation at the high wave number regime. Right, so this same idea as with high order. Right, so by doing this optimization and getting these parameters to add dissipation only at a high number regimes, we were able to get some, I think, nice results. Right, so this optimized is our version. This is the classic BGK, the classic lattice-Boltzmann. This is another version a bit more evolved. But anyway, let's see what happens, right? So if we go to a very coarse mesh, right? So this is the ideal solution, right? So this is a double periodic shear layer flow. What we get is spurious oscillations here that eventually make the simulation low. Right? It's a bit better with this improved version. I think it's a bit better with the optimized version. If we go to a more refined solution, things in this version are a bit better, but you still have some spurious vortices appearing there, and this basic version is still not very good. Of course, if we increase the resolution, eventually all the methods provide the same results, right? So, which is the exact results. But for under-resolved simulations, our optimized version provides much better solutions, even on coarse meshes. Right, of course, this can be applied also to turbulent flows and in a box, like we've been seeing. And what we get is that we are, with our optimized version, we get the right trend, the right slope, whilst there was some accumulation of energy with other methods. Right, we're doing that also with finite volume window schemes, but I'm not going into the details here. Right, very briefly on our acoustics. One of the latest developments is to see the effect of tripping the boundary layer. So for this, we have implemented this way of including tripping in boundary layers, but for airfoils, right? And what we're seeing is that, okay, there is an effect of the polynomial order, of course, so we get the directivity is right. And then when we sample the some pressure levels, we get some convergence in terms of polynomial as we increase it. But I think what's more interesting is that what we're looking into now is that the effect of this tripping, right? So if we don't do any tripping, the directivity looks almost like a monopole source directivity, whilst when there's no tripping, there's natural transition, let's say, we get this the cardioid type of directivities. So this is something we're doing during these days. Right, so I still have, I think, 5 to 10 minutes to talk about the acceleration techniques, right? So that's going to be quick because we're accelerating, right? So a few things we are looking into. One thing is we talk about the potential of increasing the polynomial order, right, to get more accurate solutions. But of course, there's regions in the flow field where you don't want to include the polynomial because there's nothing happening, right? So these are these regions here, for example, for a flat plate. What you want is to increase the polynomial order only in the regions of interest, right? So maybe close to the airflow. So the way we do that is we use truncation error. Okay, the truncation error is very easy to understand, I think, at least for steady state, and I'll show you in a minute. So if this is our Navier-Stokes equation, Navier-Stokes system, what we will consider only steady state, so this is 0, so we get this is equal to 0, and the truncation error by definition is this tau n, where we have the discrete operator, or the discrete Navier-Stokes equation, and we plug in the exact solution minus the exact operator where we have plugged in the exact solution. So in this case, this is 0, right? So the truncation error becomes only the discrete operator with the exact solution. Now, the exact solution, we don't know. That's what we're looking for. We don't know it. So what we do is we approximate the exact solution with a finer polynomial, right? So we get a finer polynomial UP, and we plug in coarser operators, right? And by doing that, we're able to plot this kind of figures, right? So what we see is we have solved for this simulation. So here we get UP, right? We solve that simulation. And then with this simulation, we don't need to solve other things. We only need to plug this into the coarser operators, right? This is what we do. And we do it for this operator, for this operator, for this operator, for all these operators. But we don't need to solve all this. We only solve once, okay? If we do that, we know that the truncation error decreases exponentially. So we know the slope of this curve, right? Which means that we can extrapolate, right, to get a particular tolerance, a particular error, and we know exactly the polynomial order we need to use, right? So if we do that, that can be, in fact, done in each direction. So if we have a three-dimensional flow, we can do it in each direction, and we can guess the polynomial necessary in each of these directions. Right? If we do so for two-dimensional cases, we get a reduction, substantial reduction on degrees of freedom that we need for a more accurate solution compared to doing a uniform polynomial order. And also we can couple this to multigrid. So multigrid, the idea of multigrid is just to use different meshes, right, to speed up the computations. And this is what we need here. We need different meshes to guess the truncation error, to guess the polynomial order we need. Hence, if we can combine both ideas. So what we did is we embedded our adaptation technique into a multigrid method, right? So what we do is we do a multigrid where we need different meshes, and because we have that for free, we can guess directly the truncation error, right? And if we couple everything together, adaptation with multigrid, we end up with accelerations or speedups of 800 with respect to doing the traditional uniform P, etc. Right, so it's interesting. We were always asked by the reviewers, what's the advantage of using truncation error if one can use adjoints? One can use adjoints. So in adjoints, what you do is you select the error in a particular functional, say the drag. I want 10% error in drag, and thanks to this, you can get an adapted mesh. Right? So, however, in adjoints, you ensure that one particular functional will be better, will fit this error that you're selecting. You don't know anything about the other one. So this drag or other functionals, the lift, might increase, whilst the other one decreases. Right, we were able to show theoretically that the truncation error, which is this guy here, controls all the functionals, right? So if you decrease the truncation error, you decrease this, you are decreasing all the errors in all the functionals at once, right? So this is kind of an advantage. Of course, you have to pay the price of a few more degrees of freedom, but you are decreasing the errors everywhere, let's say. Now, thanks to this, we think we can make this link. We can link the truncation error to a particular error in a particular function, right? So, and this is what we are developing now. So we are trying to finish this idea where adjoint advantages, which is pointing a particular error, can be linked to the truncation error, which has not been done. Right, I'm almost there. Just want to mention perhaps a couple more things. Right, so coming back to the energy stable scheme, what we realized when we're using these energy stable schemes is that we needed to use the Gauss-Lobato points. And if we use the Gauss-Lobato points and we look at the matrices arising from these Gauss, the classic Gauss or the new Gauss-Lobato points that arise from using energy stable schemes, we see quite different patterns in the linking between elements. And in fact, this can be exploited to use static condensation techniques, which are well-known techniques for hybridized discontinuous calorific methods and others. And by doing this analysis, we saw that, in fact, the Gauss-Lobato version of DG was very, very similar to HDG, to the hybridized discontinuous calorific method. Only you need to select some particular fluxes, right? And we could use that in our advantage for solving, right? So this static condensation provides faster solutions that just consider the classic system. Right. Of course, we also look at doing that with iterative solvers. So that was with direct solvers. We saw what was happening with iterative solvers. And the conclusion, I'm just going to jump ahead because I'm running out of time, is that static condensation is good for polynomials order, let's say, beyond 3, right? So for very low polynomial orders, the cost of creating this static condensation matrix, where you have to reorganize degrees of freedom in the matrix, doesn't pay off. But when you go to high enough, which is 3, it's not very high, polynomial orders, then it pays off to do this process, because then you gain on the efficiency of the solver, right? And the preconditioning of this solver. Finally, I'll finish with multigrid, a couple of ideas on multigrid. As you know, multigrid goes from very fine level to coarser levels. And in the coarser levels, what you do is you get rid of the low frequency errors. Okay, there's various ways of doing multigrid. There's V cycles, W cycles, and full multigrid. They're slightly different, but I'm not covering that now. But I'll show you examples of things we're doing with each of these techniques, right? So, for example, one possibility, it's very difficult to know when you use, when to use V cycles, when to use W cycles. It's very difficult. There's many parameters in the multigrid. They're very efficient on solving the problems, but they're difficult to tune. Okay, so one possibility that we're proposing is to use the idea of non-modal analysis by Fernandez et al., which you can find for multigrid methods in our paper here. And this gives us a parameter that tells us how the dissipation is acting at different wave numbers, right? So these are the type of curves we get with this nonlinear, we get the dissipation, right? And the wave number. Right? And we can apply that to our V or W cycles to see where we are applying dissipation, which cycle and which combination of levels, etc., of the multigrid is providing us the best damping, right? And what we want here in this particular setting is a lot of damping, because the damping gets rid of the errors in multigrid, right? So what we see is that when you combine W cycles with HP, so that's levels in polynomial and also in H, so different H meshes, different number of triangles, we get the best performance for this particular case. Right? Of course, this can be done in multiple dimensions, and again, in multiple dimensions, we get the W cycles are a bit better than the rest. Right? So this is the average dissipation. Right, so some conclusions. I think we have higher order methods that are fairly well developed, compressible, incompressible, etc. We have linear increase in cost when we have exponential decrease, or in the error, which makes them usable. We are adding a lot of multiphysics, so we can handle a variety of problems, and we are still working on acceleration. Okay, acceleration. We have some ideas on how to do acceleration, and that depends on the problem and how you set up the problem, but we have a few ideas on how to accelerate those. Just two final slides about the things that I haven't talked about, right? So we also work in the department on doing wind turbines, right? And we have work on acoustics, reduce other models for wind turbines, and trying to stabilize the wake in wind turbine settings. We also work in sensitivity, stability, and flow control, and we use sensitivity to try to explain some physical phenomena, right? So for example, the more stable flow on a round flat, on a circular flat plate driven cavity, or well, things like that. And more recently, which we think is kind of more interesting, is we are able to couple this sensitivity analysis, which provide the regions of the flow that have to be perturbed to get a more stable flow. We have coupled that to optimization, right? And we have shown that we can get surface modifications that stabilize the flow in buffet phenomena, so just by adding some bumps between the shock and the separation region. And we are able to linking it with optimizers to get more stable flows in an automatic kind of way. Right, so this ends my talk. I think I still have 5 minutes. Yeah, so I'll take any questions now. Thank you.
Thank you for great talks. I open the floor for questions. If you have any question, please unmute yourself and ask your question. While people gathering data out, I just might have a short question. Did you test your code, the speed of your code, with other existing code?
We are in the process of doing so.
Okay.
Yeah, we are not too bad. We're not bad. I mean, with other high order codes, of course.
Yes. And do you see in the near future is going to be like a free access software, or is it going to be restricted access in a license?
I think we have no problem. We have shared the code with other researchers, with other individuals that we know. So we're happy to talk and share it. We are not so sure about making it available without asking anything, because then you get emails from people you don't know, and we don't have that much time. We are a small group. Yeah. However, on a researcher to researcher basis, we're happy to talk and to share it.
Thanks. Any question? I might have one more question. About your boundary condition, when you said you need to specify them accurately, how are you going to do it for different polynomial? Is it going to be interpolation at the boundary layer? How are you going to impose?
You mean with the immerse boundaries? Or?
Yes, immerse boundaries.
So so there's various ways of doing that. When you add so this particular version of immerse boundaries works as this, no? So you penalize, or you set the velocity inside the body to 0, let's say, if the body is not moving, through body forces, right? So you don't need to specify any boundary conditions there. So this is just setting the flow field. Now, the exact boundary you need when you are post-processing the results and you want to compute there the lift and drag and everything. So then you have to reconstruct a boundary where you do your integration, right? And for this, you have various ways of doing it. So one possibility, which is, we check various ways, but one possibility is to just do interpolation. So you know the flow, you take a point at the flow field, you take a point inside your body, and you do some type of weighted interpolation to get the boundary right.
Then how you are making sure that the boundary condition is imposed correctly? Like, assume it's wall, it should be 0, and you have a grid inside the boundary, and you have a grid in the flow. And if you're interpolating, it's not necessarily going to be 0 at the boundary.
That's correct. So in the more general setting, we use well functions, right, for turbulent flows. So in well functions, for example, you don't need, so you only need the share at the wall, right? So, and for this you use the well function. So just by sampling the point outside, you are able to infer the shear stress at this fictitious wall, and this is what you really need for your turbulence, for your drag computation. Now, it is true that it's not easy to get the right values, and for this you have, especially what's not easy, it's where you have to sample the solution. How far you have to go to get the unperturbed kind of flow field, realistic flow field that gives you the right value at the boundary, right? And for this, well, you have to try, and well, we came up with some rules, but it's not the absolute truth. It's some rules.
Thanks. And maybe one more quick question about your mesh tools. Do you able to use other mesh generators to combine or link to your code, or is it going to be independent?
Well, we don't have any mesh generator which is our own. So the mesh generators we use are we use Gmesh,
yeah,
generator, and we also can use other linear mesh generators, and then we couple that with Hopper, which is a tool that curves the boundaries of your thing that was developed by some people in Germany, and we use this tool. So we generate linear meshes with any solver. I think the classic format is CGNS. We throw it into this Hopper tool, and that comes back with a curved mesh. It works quite well, not all the time, but it works quite well. And if not, Gmesh, it's also what we use.
Is it the same thing as NEC 5000? Then for each specific grid points, you're telling whether it's boundary or inside the computational domain. Is it right?
Yeah, I think you have to distinguish that. Yes, I mean basically it takes boundary conditions and curves the boundary conditions. Okay. So the ones you want. So you have to specify that. But Gmesh allows you to have curved boundaries as well. So in the latest versions of Gmesh, you can have curved boundary conditions with a polynomial I think it's whatever polynomial.
If there is no more question, I might thanks our speaker because we might go for another seminar. Thank you again. That was a great talk and
thank you. So if you're interested in the solver